Hello again and welcome to another GCSE Computer Science Theory lesson. This video is going to be on Unit 3, Compression. So first up is the simplest form of compression you'll come across. It's known as run length encoding, and I'm just going to give you an example exam question. So in the exam they could say compress this binary string using run length encoding. And to do that we just count the number of zeros, which is 4, so we're going to write down 4, 0, followed by 4 ones, which is 4, 1, followed by 8 zeros. So we've got 8 zeros grouped together there, so that's going to be 8, 0. A common mistake that a student could make during the exam is they could mistakenly say 4, 0 followed by 4, 0. This is a trap to try and catch you out. It is actually 8 zeros. Those spaces are just there for formatting purposes. Another scenario where they could ask you about run length encoding is using some text or a string rather than binary digits. So in this case it would just be 4A, 4Q, followed by 4A. By the way, if you wrote these the other way around, so for example if you wrote 0, 4 followed by 1, 4 followed by 0, 8, that would still be correct as long as you were consistent with your answer. Another important thing to be aware of with run length encoding is that run length encoding does not always make the file size smaller. Let me give you a scenario. Let's say we had to compress this code using run length encoding. This is going to make the file bigger if we try and compress it. So we would end up saying, well, we've got 1, 1, followed by 1, 0, followed by 1, 1, followed by 1, 0, and so on. So run length encoding is not a perfect method for compressing data. In some cases, it can actually make your files bigger. Alright, so the final form of compression you need to be aware of for the exam is known as Huffman trees. Okay, so here's an example that I've pasted into Microsoft Paint. So Huffman trees. There's only a few small things you need to know about them. You need to know that when we go down to the left of the tree, we call that a 0. And when we go down to the right of the tree, we call that a 1. So left is 0, right is 1. So if we were using this tree, and by the way, the tree is going to be different depending on the words that you're compressing, but in the exam, they will most likely give you a tree that's already been made. If they said in the exam, we want you to give the Huffman encoding for the word oil. Let me make that a little bit bigger on the screen. You guys see? So give me the Huffman encoding for oil. Well, first we represent the letter O in Huffman encoding, which is 0. Could we go down to the left? No, I tell a lie. We go down to the right. So we go 1, 1, 0. So right, right, left, 1, 1, 0. So O is 1, 1, 0. I is going to be left, right, right. So left, right, right. So that is 0, 1, 1. And finally L. So L is by here. That is perhaps the most tricky one in our list. We are going to go right, left, right, left. So the Huffman code for L is 1, 0, 1, 0. So there we go. There is the Huffman code for oil. Now, why is Huffman so good? It's complicated for sure, but why is it so good? Well, let's take oil. In ASCII, each character is represented by 8 bits. So that would be 8 bits times by 3, which is 24. So ASCII for oil would take 24 bits. 24 bits. But this Huffman coding is only taking 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Only 10 bits. So by using Huffman encoding in this example, we have just saved 14 bits of data. Okay, so next we're going to make our own Huffman tree. Now the exam specification for AQA has been updated that states that students should be able to make their own Huffman trees for a given piece of text. So this is the example of text we're going to be using. Now, first things first, we need to create a frequency table for all of these letters. So for example, N appears 9 times in this text, A appears 6 times, I appears 6 times, T 5 times, the space character appears 3 times in this text. And you don't have to do this, but it helps to put them in order. So list out all the frequencies and put them in descending or ascending order. Okay, and then I'm going to copy this into Paint and follow on from here. Now, what we need to do is start grouping together the smallest pair. So what I mean by smallest pair is 2 and 1. So 2 and 1 add together to make 3. That is the smallest pair we can make. So I'm going to delete that, get out the old paintbrush. Do excuse my sloppy paint skills, and call that 3. Now we're looking for the next smallest pair. Now, some of you might be saying it's 3 and 2. That is correct. This is also correct, 2 and 3. So these two have now become a new pair. So 2 and 3 is correct. These two are correct. Going for either of these is correct, but to keep things simple, I'm going to start from the right and just join these ones up. So there we go. And that makes a total of 5. And so next up, we're going to join up another pair. So this is now the smallest pair, 3 and 3, which makes 6. Okay, so the next smallest pair is going to be 5 and 4, which makes 9. In fact, I'm just going to tidy this up a little bit. Tidy it up a bit. There we go. Okay, and now we're going to be looking for the next smallest pair. So is it 6 and 9? Well, that adds together to make 15. Is there anything smaller we can add together to get 15? There is. We can add together 6 and 5, which gives us 11. So 6 and 5, which will give us a grand total of 11. And what next? The smallest pair now, which would be 6 and 9, which gives us 15. So let's join those up. And I'm just going to pause this video while I neaten up this diagram slightly. Okay, there we go, that's much neater. So we'll carry on. We need to find the next smallest pair. So we can do 11 plus 15, which is 26. I think we can do smaller than that. What about 15 plus 6? That's 21. I think we can do smaller. We've got 15 here if we add together 9 and 6. So there we go. So that gives us 15. And now the next smallest pair is going to be, well, not 15 and 15 because that's 30, because we can have 26 by here. So we're going to put these together to make a new pair. What was that again? That's 26 that makes in total. Let me just move this down so I've got more space. So that's 26. And then finally, we've got nothing left but to join up these two values, so 15 and 26. We just join those up together. So there we go. And I'm just going to pause this video one last time just to neaten things up. Okay, there we go. I've neatened it up, and there you have it. There's your completed Huffman tree. Now, if you wanted, you could neaten this up further. So here's what I made earlier. This is actually just a neatened version of this tree. So I'm going to use this one from now on. And now we're going to start filling out the Huffman values for our text, which was this. And all we need to do for this example is look at n. So n is going to be 0, 0, because left is 0 and right is 1. So n is going to be 0, 0. O is going to be 1, 1, 0. And the space is going to be 0, 1, 1, 1, 1. I is going to be 0, 1, 1. N, again, is going to be 0, 0. T is going to be 1, 0, 0. E is going to be 1, 1, 1, 0. E is going to be, no, we've already done E. R is going to be 1, 1, 1, 1, so 4 ones followed by a 0. And I'm just going to pause this video and complete the rest for you. But before I complete this for you, I just want to fill out an index or a dictionary for all of these values. So n is going to be equal to 0, 0. A is going to be equal to 0, 1, 0. I is going to be equal to 0, 1, 1. T is going to be equal to 1, 0, 0. O is going to be equal to 1, 1, 0. L is going to be equal to 1, 0, 1, 0. The space character is going to be equal to 1, 0, 1, 1. E is going to be equal to 1, 1, 1, 0. R is going to be equal to 4 ones and a 0. And Z is going to be equal to 1, 2, 3, 4, 5 ones. Now, you may have spotted a pattern here. N is the most frequently occurring letter in this phrase. Z is the least frequently occurring. It is no coincidence that the most frequently occurring letters use the least bits, whereas the most occurring ones use the most. That's part of the design of a Huffman tree. It's a method of keeping the storage space down as much as possible. Okay, so here's a completed Huffman code for the tree that we just made, and it is only 128 bits for this entire phrase, whereas the uncompressed ASCII takes up 328 bits. So we can see that Huffman is extremely effective in reducing file sizes. Here's the thing. The AQA exam specification has been updated recently to say that students must need to know how to make Huffman trees and create Huffman code for a given piece of text. I find it highly unlikely that the exam board would get you to do this in an exam. The reason why is because drawing that Huffman tree and writing out all of this binary code takes a very, very long time. It's going to take most students about 30 minutes to do this. I very much doubt the exam board is going to waste a student's time by giving them 30 minutes of work to do for such a small part of the overall content. So in that case, I can only suspect that the exam board is going to ask questions in a certain way on the exam that require students to be aware of this, but don't necessarily involve them completing these steps. Let me give you an example. So take this question. We've got some text here, and it has been compressed and made into a Huffman tree. However, there are 2 letters missing. The question is, identify which letters are missing from this Huffman tree and identify the correct position in which they should go in. To answer this question correctly, you need to know how Huffman trees work, and you need to know how to make them. So just pause this video and have a think about it. Unpause when you're ready to continue. So the missing letters are A and H. A will be going at the top of our tree, whereas H will be going in at the bottom. But why? Why is this happening? Well, A is the most frequently occurring letter in this sequence, so it's going to go at the top of our tree. Huffman trees are designed so that the most frequently occurring character goes at the top, so it uses the least number of bits, and therefore space is used more effectively. H is the least frequently occurring letter in this sequence, so it makes sense for it to go at the bottom. And there you have it. That's everything you need to know about Huffman trees.